Transformers. AC power is easy to be altered in voltage. You can't do this very easily with DC power. Transformers are the gadgets that enable us to change voltages from either high to low or from low to high. And let's see how that process works. So shown here are two coils, one in green and one in brown. And you can see that if we pass a current which is changing, of course, within the coil 1, it's going to create a magnetic field in the middle of this solenoid or coil, which of course will also thread through the green coil, which is coil 2. And let's say coil 1 has N1 loops and coil 2 has N2 loops. And the flux that is produced by that is threading through coil 1 need not necessarily be the same as the flux threading through coil 2. So in the particular example shown here, it looks like some of the flux coming from due to the magnetic field from coil 1 indeed is not connected with coil 2. But in any case, there is an effect, and let's see how that works in a real transformer. So in a real transformer, you have windings on one side, which are called as primary, and there is a source of EMF. It's an alternating current EMF, so it produces voltages that shuttle back and forth. So half the cycle it's positive here, and half the cycle it's negative. And this alternating current produces, of course, an alternating magnetic field. So half the cycle, its magnetic field is pointing upwards, and the other half cycle, the magnetic field is pointing downwards. And these primary coil windings are wound around a iron core, which is shown here in the shape of a square, roughly. Donut. And because of the properties of iron, all of the magnetic fields that are produced here are bent and carried over to the other side. So essentially, the flux, which is the product of the magnetic field times the area here, is preserved and carried to the other side. Now, on the other side, we have a secondary coil, which in general has a different number of turns, and that picks up the changing flux and produces a secondary voltage on the right side. Also, of course, there is a secondary current. So what we're going to figure out is what is the relationship between the primary voltage and the secondary voltage, and what is the relation between the primary current and the secondary current. So we start first with the instantaneous flux, which is contained within this iron core. And since the magnetic field is threading through NP loops on the left-hand side of the primary coil, we can write the rate of change of flux is d phi b dt times the number of turns on the primary will give us the induced EMF. So this would indeed be the voltage that we are applying on the left-hand side. The same flux passes through the secondary as we stated earlier, and therefore we are able to write the equation that V sub S, the induced voltage in the secondary coil, is equal to N sub S, the number of turns in the secondary coil, times the rate of change of flux, which of course is the same as before. So if we divide equation 1 by equation 2, we can see that the secondary voltage and the primary voltage are related in a very simple manner to the ratio of the uh, number of turns in the secondary to the number of turns in the primary. So if we construct a transformer with a lot of turns in the primary and very few turns in the secondary, as shown in the picture here, that would give us a step down effect. So um, Ns is less than Np, and therefore Vs is less than Vp. If we apply a voltage of 110 volts, for example, we could get something like 5 volts, which would be needed to charge your cell phones and gadgets like that. Most real-world transformers are extremely efficient. The iron core does not dissipate much heat. Um, the copper windings have very little resistance in them, and the iron cores are not made out of solid iron. In fact, they are made out of plates of iron so that the eddy currents don't have an opportunity to complete a circuit and thereby dissipate some of the power. Now, as far as the power itself is concerned, we said that the voltages can be either stepped up or stepped down, but there is a price to pay. For example, if you step up the voltage, it doesn't mean you'll get the same current. So the key idea here is that the power has to be conserved. So the power going into the primary has to be equal to the power coming out of the secondary in a 100% efficient transformer. So therefore, we can write the relation that the current times the voltage on the primary side is equal to current times the voltage on the secondary side. And so if you use the earlier relation that we got between the secondary and the primary voltages and how they are connected with the number of windings, you see that it's inversely related. So in other words, if you have a smaller number of turns in the secondary, you get a larger current in the secondary.